Hello, I am Shreyas Donti, and today I will be exploring my research topic being investigating data transfer performance bottlenecks and optimizations in modern programmable OpenGL. So, why does this topic matter? You see, performance is a major concern when designing real-time graphical applications such as video games and real-time physics simulations. Displaying thousands of objects on the screen can be incredibly performance intensive and cause applications to run really slowly. For example, a game might need to store the information of and draw thousands of grass patches like in the given image, while also processing things like lighting and movement for each grass patch. Developers have recognized this issue, have constantly strived to address the many performance bottlenecks that their application might be facing. Today, I hope to be exploring one such performance bottleneck caused by the data transfers from the CPU to the GPU. I hope to identify methods and solutions that are used to minimize the number of data transfers and that are available for implementation in modern OpenGL. I hope to understand the trade-offs and use cases of each optimization technique so that future developers are better informed of which techniques best suit them. Now, first, what is the data transfer bottleneck? To understand that, we must first understand how applications handle graphics. First, an application will store the information for each object in the current scene, such as size, position, and color. This data is referred to as vertex attribute data in OpenGL. Each object is drawn on the screen by transferring that data to the GPU via a rendering API. Before sending that data, however, the CPU also configures the GPU's render state, which contains information such as what shaders, which are computer programs used to manipulate graphics, are being used to prepare it for receiving the data. When this vertex attribute data is received by the GPU then processes this data by using what is known as a graphics pipeline and converts this data into pixels on a screen. Now, instructions that are used to send this data from the CPU to the GPU are called draw calls. Each draw call, however, can be performance intensive on an application due to two reasons. Sending multiple draw calls can slow down an application because the data bus has a limited bandwidth and can only transfer so much data at any given time and at a certain rate between the CPU and the GPU. Furthermore, it can be expensive to reconfigure the render state of the GPU every time you send a draw call to the GPU. Now here's a graph I produced from the results of a simple application that shows the relationship between draw calls and FPS. Here, I increased the number of primitives I was drawing each frame, and with one primitive being one draw call. And I noted that the average FPS of my application greatly reduced as I tried to draw more and more primitives. From these results, we can identify that there is a definite performance bottleneck from creating a lot of draw calls. Now that we've identified the data transfer bottleneck, we must also understand what I mean by modern OpenGL. You see, OpenGL, or the Open Graphics Library, is a cross-platform graphics API for rendering 2D and 3D graphics that was initially designed by the Silicon Graphics Group company in 1990 and early 1991. Currently maintained by the Kronos Group, a consortium of over 150 companies devoted to maintaining royalty-free standards in the field of computer graphics. OpenGL is one of the most commonly used graphics APIs today due to its portability and long history. Throughout its history, however, OpenGL has seen a lot of revisions and a lot of new versions. And one of its biggest changes was the transition from an immediate mode API to what is known as a retained mode API. Legacy versions of OpenGL, which are versions before version 3.0, implemented what is known as an immediate mode API. You see here, an immediate mode or API of legacy OpenGL would have the scene data for an application be stored on the client side, the user application. And this data would be transferred one command at a time using draw commands, such as glbegin and glend, and will be transmitted to this GPU. However, this is inefficient because it required a lot of draw calls to be made, a lot of function calls to be made to the API to transmit that data from the CPU to the GPU. Instead, developers have opted to use what is called as retained mode or modern OpenGL. modern OpenGL, where all of this data is stored on the GPU and can be transmitted to a simple function, which is GL draw arrays or GL draw elements. You can see here in the diagram, the scene data is stored on a server side rather than the client side, and it's stored in a VBO. Now that we've identified what modern OpenGL is and the the data transfer bottleneck, we can identify solutions used in OpenGL and are applicable to multiple rendering APIs that can be used to address the data transfer bottleneck and minimize the number of draw calls made. Now, our first method that we'll be looking into is batch rendering, which utilizes the properties of a vertex buffer object to store the data for multiple objects in a single array and send that data to the GPU in a single draw call, which is referred to as a batch. With this batch rendering technique, vertex attribute data for tens of thousands of objects can be stored in a few arrays and sent in a few draw calls. Batches can be either static or dynamic, where static batches have data that is set only once and rendered multiple times, whereas dynamic batches have the data be modified multiple times on the CPU, but is still sent to the GPU in a few draw calls. Now, the pros of batch rendering are easy to see. It is extremely quick, especially when rendering static batches, as the data doesn't have to be modified every time. And it can greatly reduce the number of draw calls. However, batch rendering involves allocating a lot of memory to store all of that object data. It can be inefficient if a small number of objects are rendered, or if objects of multiple types are rendered, because batch rendering can only render objects of similar types with every batch, meaning you can't render squares and lines with a single batch. You need two different batches for them. The use cases of batch rendering are for drawing multiple static objects that don't change during the runtime of an application, or for applications that render a medium number of objects. Now, a second technique would be geometry instancing. In OpenGL, draw calls are generally made with the aforementioned GL draw arrays and GL draw elements. These commands, however, only draw a single instance of an object. To draw multiple instances of a similar object, you use the commands gldraw arrays instance and gldraw elements instance, while specifying the number of objects to be drawn. However, these objects won't have their own individual data because that isn't specified. So by using separate vertex buffer objects, the vertex attribute data for a single object and its dimensions can be stored in one vertex buffer object. And the second vertex buffer object will store the data for every individual instance of the object, such as the position and scale of each object. For example, going back to our previous scene, which is the patches of grass, the dimensions and color of the grass patch can be stored in one vertex buffer object. And via geometry instancing, a second vertex buffer object will store the individual positions for each and every one of these grass patches, and that data can be transmitted using geometry instancing. Now, the advantages of geometry instancing are that it's useful for drawing extremely large numbers of similar objects. However, it cannot be used for drawing different types of objects. And of course, the use cases of geometry instancing will be for drawing tens of thousands of the same object, where batch rendering would not work due to the heavy memory requirements batch rendering would need. Now, our final technique would be visibility culling techniques. This is a category of techniques which are used to make rendering efficient by culling objects that a user cannot see in the current frame. These techniques are frustum culling, which is named after the view frustum of a virtual camera used to show perspective in a 3D environment. This culling method removes all objects that are not within the camera's field of view, also known as the FOV. Then there's occlusion culling, which stops the rendering of objects that are obscured by other objects in the scene. And then finally, there is backface culling, which renders the front-facing polygons composing a 3D object while discarding the back-facing polygons. In OpenGL, this can be simply done by invoking the GL cullface function. Now, the pros of culling techniques are that they can remove the redundancy and reduce the number of drawn objects. and they complement and can be implemented on top of batch and instance rendering. However, they may not always be effective because some applications may not have a lot of objects out of camera view. The use cases of these techniques depend on what technique you're using. Occlusion and frustum culling are suitable for any application with a camera, as 2D applications can use these culling methods with an orthographic camera. Backface culling, however, only works for 3D applications. Now that we've looked at all of these techniques, we can conclude that developers of performance-critical applications and OpenGL programmers have to minimize the number of draw calls they make to the GPU to make their applications faster and more performant. Developers should consider each of the given techniques and methods and implement them in their own programs, but should also consider which technique best suits their needs. And with that, I'd like to conclude and thank you for listening.
Hi, I'm Milind, and I'm a senior at Mountain View High School. And I'm going to be talking about my research on quantum machine learning applied to image classification. So to start off, we're going to go into some background of quantum mechanics. And the gist of this is that small particles, such as electrons, are not actually fixed in one position in space. They're wave-like, which means they're spread out in many positions at the same time. And to illustrate this concept, there was an experiment called the double slit experiment, where there's a wall with two slits. Here you can see the image at the bottom of the screen. And these two slits had particles fired through them. And then these particles would hit a detector screen at the back, and you would observe the pattern that they make on the detector. So if you fire normal particles like bullets through these two slits, you'll just see two bends corresponding to where they could go through. But if you have a wave, like let's say you have a light bulb in front of these, the two slits are going to split the wave, and the wave will basically, it's called diffracting through these slits, and it'll act as if two new waves were created from each slit. And then these waves will do something called interfering with each other, which will cause this pattern on the back. So if you have a classical particle, you'll see two bands, whereas if you have a wave, you would see this thing called an interference pattern. Now, if you fire small particles like an electron, you'd expect to see the two bands just like a bullet because you think it's a particle. However, each particle itself acts like a wave and diffracts through these two slits, which actually causes this interference pattern. So that's called superposition. Being in many places at once. Now, another quantum mechanical principle is entanglement. And this basically means that particles like electrons can influence each other non-locally. So for example, if you had an electron here on Earth, and then you had an electron, let's say across the universe, suppose this one on Earth were to change, that change would be reflected in the electron across the universe instantaneously. And these properties, as Albert Einstein said, are spooky because they are, and this is just how the universe works, and we have to accept that. But they can be really useful and applied to quantum computing. So quantum computing is where you take these properties and you apply it to computing, and this is really helpful. So classical computers will store information in bits, which are either zeros and ones, but quantum computers have qubits, which are in a superposition of 0 and 1. So just like how electrons could be in a superposition at many places at once, these qubits can be in a superposition of the state 0 and 1. So like a normal bit is just either 0 or 1, but a qubit is both 0 and 1 at the same time. And this gives quantum computers a lot more power. So if you add one more qubit to a quantum computer, due to entanglement and superposition, the quantum computer will become double, it'll get 2 times the power. So let's say you have 2 qubits in a quantum computer, and then you add a 3rd qubit, it'll double in power. Now, if you add a 4th qubit, it'll double again. If you add a 5th qubit, it'll double again. And this just shows how if you keep getting more qubits in a quantum computer, it'll definitely surpass classical computers in certain problems. And that's the future. But right now, many quantum computers don't have that many qubits and are not completely reliable. So quantum computing code has to take that into account and optimize for it. So one application of quantum computing is quantum machine learning, which is basically teaching a quantum computer how to solve a problem, just like how normal machine learning is teaching a classical computer how to solve a problem. This problem could be like asking it if an image is of a cat or a dog. And the computer has to itself learn how to distinguish between cats or dogs given images of the two. And quantum machine learning can be better than classical machine learning in certain cases because of it takes advantage of superposition and entanglement to do so. So my quantum machine learning research project was applying quantum machine learning to classify handwritten digits. And in this case, we chose just to classify handwritten 3s versus handwritten 6s because quantum machine learning is still relatively new, and we just wanted to apply it to image classification, not necessarily the hardest image classification problem. And we use a special type of neural network called a quantum convolutional neural network. So in classical machine learning, a convolutional neural network is usually applied for image classification because what it does is it detects different features in an image. And this could be like, let's say, the top of a 6, or maybe like the curvy part in the 6. The computer has to figure out what features to look at in 3s or 6s. And it'll pool these features together and figure out if a picture is of a 6 or a 3 in this case. And a quantum machine learning, quantum convolutional neural network would work in a similar way, but it would just be using qubits. So one problem I encountered is that these images are large for a quantum computer. So even though this image is tiny for a normal computer, like the one you're viewing this on, for a quantum computer, one quantum computer can't even store this image, can't even store one image. So I had to experiment with ways of cutting the size down, like pre-detecting features and other ways, but I came to the conclusion that it's best just to blur these images and downsize them so that they can easily fit on a quantum computer. So the results of my research. When I tuned the quantum neural network to its best performance, it could classify images with 87% accuracy. Now this seems good, but I didn't really have like a way to know how good 87% was. So I made a classical neural network that was a fair comparison, which basically means that it had the same number of parameters as the quantum neural network. And it could classify with the images with 90% accuracy. However, it required 10 times the amount of training data, which means that I had to give it 10 times the number of pictures of 3s and 6s before it could figure out how to distinguish between the two. So this means that quantum neural networks can actually learn much faster. And this is likely because of how my quantum neural network took advantage of entanglement and superposition. And when the classical neural network had the same amount of data as the quantum one, it was not accurate at all. It would vary from like 70% to 80%, but it would not be consistent. So given that the quantum convolutional neural network was comparable to the classical one, this means that quantum convolutional neural networks could likely be applied to other image classification problems in the future. And especially as quantum computers increase in power, we're going to see that like harder image classification problems, like maybe comparing cats or dogs, right? That's much more complex than comparing 3s and 6s, will be able to be solved with quantum computing. So yeah, if you have more experience with quantum computing or quantum mechanics, I encourage you to take a look at my research paper. But thank you guys for viewing this talk, and I hope you enjoyed it.
Hi, I'm Matthew Grupenhoff. I'm going to be talking about an attempt to train a gated recurrent unit neural network with a cryptographic hash function, specifically the SHA-1 hash function. So these are two really distinct fields. It's cryptography and machine learning. And these are really distinct because cryptography uses functions that don't have super convenient properties in order to make them hard to break later. On the other hand, machine learning is all about finding these properties through a computer. So these are really far apart, but they're not necessarily exclusive. So what are hash functions? Hash functions can have input data that's any length. It could be 0. It could be extremely long. But the output data is always the same length. So for example, the SHA-1 function that we're using in this study is 20 bytes. And the two important properties about hash functions are that if you're given two outputs that are the same, then you can almost guarantee that the inputs are the same. And also, the thing about this is if you are given an output, you can't actually figure out what that input is that led to the output. So the research question here is, can we use machine learning to approximate one of these functions? So a neural network is a useful method of machine learning. There are these layers of neurons, and each layer has a series of neurons, and those neurons are sometimes linear, they're sometimes non-linear. Linear neurons basically multiply the state from that goes into that layer with a matrix, including some biases that it can add to get another state. And then the nonlinear ones apply an activation function on all of those values. And sometimes it combines some values through things like multiplication. So a recurrent neural network is when you take a bunch of neural networks and stick them after each other, and you have hidden state that comes out of one of those and it goes into the next one, which is how it remembers things. And then you also have inputs that go up into the neural network, and there's a different input each time, and it's usually a sequence of inputs like a sentence, and then you feed each word in, for example. And the hidden state itself normally starts at something like 0. And then the final hidden state is sometimes used to do some other processing, where sometimes each neuron in there just outputs its own output. So to build a model to achieve this goal, we want to do something similar to language translation, which typically has an encoder and a decoder. So the encoder would pass the output to a decoder. And the translation, though, that actually takes a sequence in and it creates a sequence from the decoder. But we don't actually need to do that here, because all that's needed here is just one value, which is the entire hash output. So we actually only need an RNN for the encoder part here, which is described right here. So this is an RNN. It's a special one called a GRU, gated recurrent unit. And it has a really specific architecture in there, which will be important later. But there's this embedding layer as well, which aims to just make some of the encoding of the different tokens in here more close together so it can be processed better by the GRU network. And here, a token isn't any word in the password, it's actually each character, and it converts 98 dimensions down to 49. On the other hand, the decoder is much simpler because we don't need the sequence output. So there's two versions right here. It depends on which experiment we're doing, but in one kind of experiment, there's a linear layer which just converts that hidden state down to something else. And then it normalizes these so that when those are super small magnitudes, they can be more reasonable. And then the sigmoid is applied, and this is a kind of function that takes anything from negative infinity to infinity, and it squeezes it down to a finite range. For example, this one here, it goes from 0 to 1, which is perfect because we want to output a probability when we train it later. And the other kind just doesn't have that normalization. So it just does the linear layer and then passes it into the sigmoid. So to train it, since this is SHA-1, it's 20 bytes. that becomes 160 bits. So there's one dimension for each bit. And that's a probability of the bit being 1 because neural networks are always continuous. So because of this, the error here was measured through a loss function called binary cross-entropy loss. And it has this equation right here, which is basically the average of a bunch of natural logs. And then I use gradient descent to train this. So there's the gradients of that loss with respect to all the parameters, like the weights and the linear layers. And then the parameters get changed in the opposite direction. So that would go toward the least error. And then to evaluate it, once the training is done, a different set of data for evaluation was used. And the accuracy was measured by taking the total number of correct bits, not the total number of hashes that are correct. And those probabilities are rounded to 0 and 1 in order to compare it, because it's not going to just output either of those, but it should be confident in theory. And then that ends up giving this accuracy value, which was recorded. So to test this, first, just the normalization and the non-normalization networks were run to test. And this is what ended up happening. Now, one important thing to notice here is the scale. This is 0.497 and this is 0.503. So all of these are basically just 0.5 when you look at it. So there really isn't any learning happening right here, which is strange because learning would be expected. The accuracy should be going up. And so now the next thing to see is, what are the gradients looking like? And it turns out the gradients do actually exist at first. So it is doing something, and then the gradients are just going to 0, which means if we turn up a value called the learning rate, which says how much you should change with respect to the gradient every time you want to train it, then in theory, there should be more learning and the accuracies should go up. So turning up the learning rate still has no effect. These all round to 0.5. So there was no reason to turn it up, and that's not the issue, it turns out. So now the thing to look at is the losses. So after collecting loss data, these are the summary statistics. And when the parameters are normal initialized, there ends up being a trend of going toward an asymptote as seen on the graph. And when it's 0 initialized, which was tested, then it just stays at 0.693 the whole time. And 0.693 is also roughly what the asymptote is on this graph. So 0.693 seems to be the minimum loss that can come from this. So this is strange and it's worth explaining. So the loss, the way that's minimized is by being as close to the ground truth as possible, not just from it rounding to the ground truth. So it turns out that 0.693 is the exact loss you get if the network is just outputting things around 0.5 all the time, because then the distance is always 0.5 from a truth. And that's literally the minimum loss. So as a result, you literally just can't learn SHA-1 in this GRU setup. So to dive further, I tried changing the batch sizes just to see if the gradients would change, because this could help explain what's happening to keep it from learning. And these are the average gradients, and it's clear that the average gradient did go down with batch size there. So the way this can be explained is a bunch of people fishing. If you have one person fishing, then you have a certain gradient, which is that arrow there. If you have 2 people fishing, then they're probably going to pull against each other. So then the thing ends up being smaller when they both fish that fish. And if there's a lot of people fishing, then that fish is going to get pulled in all sorts of directions. So it'll end up not being very useful to do that, which is exactly what was seen with the batch size, because each data point trying to train is basically another person pulling the fish. So one thing about all this is that SHA-1 actually has a lot of discontinuous functions in it, like it has left shifts and right shifts, and those aren't continuous because you have to cut some parts off of the number. So a different RNN that has a discontinuous activation function could work a lot better for this. So big thanks to Dr. Joe Xiao for really assisting me with this project. He knew a ton about AI. He taught me how gradient descent works. He taught me about good research practices and guided me around those common pitfalls in research. He was just really supportive in general and helpful, given that research was still pretty new to me. And also thanks to Polygens for really just matching me with this mentor and just supporting me through this project and helping in general. And thank you for coming here.
Hi, my name is Andrew, and today I'll be presenting my Polygens project, which I've been working on for the past few months, predicting soccer player market value using machine learning. As a lifelong soccer player and avid soccer fan, I hope to understand the increasing power data had in professional sports. My research goals for this study. My primary research goal was to use public accessible data to predict the market value of soccer players in the following summer. The data I used was from the top 5 European soccer leagues in the 2017 to 2018 season, which came from leagues in England, France, Germany, Italy, and Spain. One of the more nuanced things that I've incorporated was the incorporation of flow motifs, which basically serve as the essential building blocks of a team's playing style, and I'll go over this in the next slide. I wanted to compare various models of machine learning and also determine what group of data is most significant in predicting market value. One thing that was a very important part of this study for me was to build something with a practical use, and this practical use was for player recruiting. This model could find bargain players that would both fit the team's playing style and also be undervalued in the transfer market, which would serve as a good aid to try to find and scout out players to add to the squad in the next season over the summer. So what are flow motifs? Flow motifs are sequences of passes, sequences of 3 to 5 passes from a team in a possession where there's no longer than 5 seconds in between. Since passing is the most prevalent part of the team's playing style in soccer, these flow motifs zoom in on the team's playing style and then offer a way of quantifying it. There are 2 types of flow motifs which I recorded in the study, one with shots ending and one without shots. And this was inspired by a separate research study, Flow Motifs in Soccer, What Can Passing Behavior Tell Us? In the figure to the right, we can see that starting from player A passes the ball to player B, which passes it to C, which passes it back to B. The corresponding flow motif would be A, B, C, B. If it ends in a shot, the corresponding flow motif would be A, B, C, B, S, S marking the shot. Data pre-processing. For this project, since the data was not readily available, the data pre-processing took up a large chunk. I used data from 3 separate sources. First one was temporal data from all matches of all 5 leagues in the 2017 to 2018 season. This documented every single action, every single play of every single player. And this was provided to me by my mentor. The second source of data I used was season data for all players. This included data such as shots or goals, assists, yellow cards, red cards, and stuff like that. And the third data was the market value, which was from transfermarket.com. After cleaning and integrating the data, I eventually merged the data into a single data set that could be used for modeling. And here again, going into the nuances of this, cleaning the temporal data took up the largest time because I needed to filter out the extraneous features while also using Python to code to scrape the data to create the motif count data set. This ended up with a data frame with the motifs as the column titles and the player name as the row indexes, while the counts of the motifs for each of the players in the inside. The season data, I downloaded select full season stats for each league, such as goals, assists, tackles, and the market data, I filtered it to only summer 2018 and matched the values of the players. I integrated the data by merging the data together using the player name, and as my final data set, I had 54 features, including the motifs, the season data, and the market value with 15,098 rows or different players. Here we can see some examples of the flow motifs distribution in radar charts for 3 different types of players. We have Harry Kane, who's an attacker, and we can see that his most prevalent flow motif is 2-3-1, 1 being himself. This makes sense as he's an hacker. He's usually at the end of passing patterns, and this 2-3-1, the 1 is at the end. Granit Xhaka, who's a midfielder, has a different motif distribution than the Harry Kane because his is more evenly distributed amongst the rest. Also, this makes sense because since as a midfielder, he is involved in different types of passing patterns. And finally, Raphael Varane, who is a defender, is more likely to be involved in passing patterns when he's at the start, as his most prevalent one is 1-2-3, him being the 1 at the start, starting the play. A change I had to make going into modeling was to normalize the data. My initial market value was heavily skewed as most of the market values of the players were clumped towards the left, with only a few star players reaching over $100 million in market value. Running a logarithmic algorithm on all of these, I normalized the data, as you can see in the chart to the right. The first thing I integrated in my machine learning model was principal component analysis, which is an unsupervised machine learning model that takes the features that I have and reduces it down to several principal components, which reduces the dimensionality of the data set that I go into the model with. For example, in my model, I took all of the motifs, which you can see here, 1-2-1, 1-2-3, and going to 11 more to 28 motifs in total. I ran principal component analysis on them and transformed those into 8 principal components, which denoised the data by finding components of greatest importance. And some of the advantages that come with this is that it speeds up the algorithm and combats overfitting from excessive features. The first model I used for modeling was random forest regression, which is a decision tree algorithm. It used ensemble learning, which was generating results by training and averaging results from many different decision trees. And then I used the default 75-25 train test split. My second model was XGBoost, or extreme gradient boosting. This model also incorporated ensemble learning, but in this case, instead of averaging the results from different trees were added 1 at a time to fit and correct prior errors. For this one, I used the 70-30 train test split. So here are my results for both random forest and XGBoost. I ran 5 different data sets on these 2 models, and these 5 included the full data set with no changes, no shot motifs, which is the full data set, but leaving out the motifs with the shots, only season data, which was the data set without motifs, which only included data such as goals scored throughout the season, assists throughout the season, stuff like that. PCA motifs, which is PCA or principal component analysis, ran on the motifs, which I previously went over, which made my motifs go down from the 28 separate motifs to the 8 principal components. And then finally, the tuned hyperparameters for both of these models. The worst performing data set for both of these was the only season data. So without the motifs, that was the worst performing, and the best performing model was the full data. Also, for all five of these data sets, XGBoost outperformed random forest. The best performing was the full data, as the mean squared error was the least. And the inclusion of the shot motifs were important, as you can see that with the data set without the shot motifs, the error went up for both random forest and XGBoost. Inclusion of the shot motifs were important because it showed players' involvement in goal creating chances, which is a big feature of how much they are worth in the market. Here are some of my graphs of the final model, which is XGBoost with the entire data set. You can see the scatter plot to the left and the density chart to the right. Conclusions. My first conclusion was that there are clear trends to show correlation between in-depth match and season data and player market value. Passing specific data is useful in predicting market value, as the inclusion of flow motifs decreased the error in both models, making passing a heavily important part of market value. Also, XGBoost outperformed random forest on all tests, and running PCA and hyperparameter tuning are not entirely useful and even counterproductive in the efficiency and performance of these models, as it even slightly increased the percent error or the mean squared error. Thank you for listening, and a special thank you to my mentor, Ethan, for supporting me and helping me throughout the project.